Record and start. Okay, so now we're starting the review. This will be all recorded. And let's see if there's any questions to start, and then we can go to doing the practice test. So this is your chance to just ask a question or a concept you're confused on. I can also do like any sort of problem, and I can show you how to do things on the calculator. So anything you have questions on, feel free to ask at this time. You can turn on your microphone and be like, how do I do this problem? Or what was this chapter all about? Anything you want. If there are no objections, I will go on to doing the practice test, but it seems like that's what people want. So let me go ahead, and I am going to click over to my Pearson, and I'm going to bring up the practice test. Okay. We'll start off with the third practice test, which only has test final material on it. Exam aids, practice test 3, and let me look at the online stop. It's right at the 1 minute mark. So 1:15. Okay, let's go over to screen sharing right now so you guys can see what's going on. You're going to see my stopwatch. First thing you'll see. Are you guys seeing the stopwatch? Give me a thumbs up if you are. Cool. It said I'm sharing my desktop, but I guess I'm just sharing everything, and the control thing is in my way. Oh, really? I think... Well, if you want to open it once, just open it again. And now it's open because this is where we wanted to be, right underneath the Zoom meeting button. So let's move it around. There we go. Now, really, Zoom meetings, stop doing that to me. Okay, now we can get to it a little bit better. Okay, so let's scroll down just a little bit here. This first question right here, when it comes to a question, the first thing you should do is identify what the question type is. When I get to a question, the first thing I do is I look at it and I say, what kind of question is this? What could we possibly do with this data? And this data right here is from 2 stores, Store A and Store B. You could technically do one sample mean stuff with it, but it's kind of designed to be a 2 sample question because there's 2 stores. So this is a Chapter 20 question, which is a 2 sample means question. We could do confidence intervals for the difference, and we could also do a statistical test of the difference. So that's what's going on with this question right here. Important to note the notation as we go through. Let's see here. Let's open up a little notepad on the side. We're rocking some Windows 10 right now. My computer actually went crazy on me, and I had to get Windows 10. It's pretty nice. I'm liking it. So here we go. We'll put some notation on the side. We have N1, which we're calling N sub 1, or rather, let's go N. It's N sub 1 in the notation. We'll leave it at that. From Store A, we have sampled 41. There were 44 transactions at Store A, excuse me, and 41 transactions at Store B. I'm taking that from the problem itself to get the notation for it. You notice right here it says there were 44 transactions at Store A and 41 at Store B. What else do we have for this? Not too much else in the terms of data. You also know that there were a total of 15,000 transactions. That'll come into play with the 10% condition if we have to do it, because we know total monthly transactions, we can't sample more than 10% of the transactions or else we'll violate the 10% condition. So that's what that information is there for. Always kind of be like, why are they telling me this? And usually, and especially the way I write test questions, it's there for a reason. So we have this going for us right now. Even more so, we see the data itself. This actually is of no use to us. It's just a very small snip of the data. But we do get the histograms with a normal curve plotted on top. This is foreshadowing a goodness of fit test, which we can use to check the normality. Both of them pass the goodness of fit test. Just seeing what we have here, we have that we can't reject the null that the data comes from the normal distribution, and we can't reject the null that the data comes from the normal distribution. So it looks like the data is normal. It's normal enough. Good for us to know. So with this in mind right here, I'm probably going to open up a Word document here in a second so actually you can write these out. Let mu A equal the population average transaction time for Store A, and mu B equal the population average transaction time for Store B. Using proper mathematical notation, write out the null and alternative hypothesis this regional manager wishes to test. So with this in mind, let's see if there's any inclination up here. The null is going to be the easy part. The alternative is what the problem will always lead you to test. And I'm trying to scan through the problem right now. The manager wants to know, is there a statistically significant difference between the two averages? That's very important right there. Is there a difference? The difference does not imply any preference. It doesn't imply any sort of, let's see if Story is doing better because we have a new manager there, or we're doing new training. It's like, let's just see if there's a difference. So we need to write out the null alternative right now, which is easiest, best done, easily, I don't know, I'm making up words right now. It's best done through Microsoft Word using the insert equation button. We can go to insert equation. Before we do that, let's type out the null. There is a microphone next to me. So let's increase the font. Make it nice and big so you guys can see. Now we don't need to use the equation writer, I was thinking. We need to go to insert symbol and put in mu. So we have the true mean for store A equals, and let's do a little copy paste jobby right here, the true mean for store B. And this is our null and our alternative right here as I hit bold. Our null is the true mean for store A equals the true mean for store B. And our alternative can be found by doing the does not equals. The alternative is just going to be that the true mean for store A, let's add in the symbol, does not equal the true mean for store B. And we're talking in matters of truth right here. The notation right here is very important because mu is true mean. We're going to see sample means, which is our best guess at the truth. These are the true means. The true mean of store A equals the true mean of store B. And we're going to investigate this. Our null is that they're equal. Well, let's just start out assuming they're equal and see if we can find evidence of a difference. That's what we're trying to examine into. So let's go over to the question a little bit more and see what's going on. Okay. There are 4 conditions. Condition 1, I think it gives it to us. Or does it want you just to give 3 of these? I'm trying to remember how this one goes. Give 3 of the 4 conditions? Oh, that's easy. That's so much fun. So just giving 3 of the 4 conditions for all these tests, and this is where people get in trouble. The in-class class knows QQ straight enough, no outliers a little bit too well. QQ straight enough, no outliers, the plot doesn't thicken is the conditions for regression. When we plot a line, we want to check those conditions. But now we're into the realm of tests and confidence intervals, where we want to randomly sample, condition number 1. We want to make sure we sample less than 10%, condition number 2. And then we have to make a choice. The choice is whether the data is quantitative or categorical. In this instance, we have quantitative data because it's sales at a store. I believe it's sales. It's at least a quantitative measure because we have histograms. Histograms are a dead giveaway on quantitative measures. So it has to be quantitative. I'm going to double check to make sure if it's sales, store A, store B, and transactions. It's number of transactions, which is quantitative. If it's a histogram, if there's histograms, it's quantitative. That's a given. So with this in mind right here, the third condition is the large enough condition, or we can call it the nearly normal condition. It's that the sample size is large enough for the distribution of means to be nearly normal. And that means that we can use the empirical rule. We want to use z-scores. We want to use the normal curve to describe this. So if we don't have a large enough sample, the empirical rule will not apply. The empirical rule is that the distribution of single observations could look all weird, but then the distribution of means gets tighter and more normal as we increase the sample size. Increasing the sample size, distribution becomes tighter and more normal, and it's not called a theorem lightly. It's the central limit theorem. Like, it's been proven. I've had students be like, how do you know this? Are you sure? And they're like, no, it's a theorem. It's mathematically proven to be true. So we know that the distribution of means will be normally distributed, and it's a theoretical distribution because we can't get all distributions of sample size mean whatever. Condition number 4 would be that the 2 means are independent. This means that mean number 1 does not influence mean number 2. So we can't say that, oh, store A is going to influence store B. And if there was something like store A was constantly running specials and store B wasn't, you could talk about how it's not really a good test to be done because there's going to be an influence. Or maybe people will get a coupon at store A to use at store B. So we don't know. We don't have any inclination of that. It seems like the 2 stores are independent of each other. Got some iced tea tonight. I had a blue drink one time, and people were like, "What, blue drink?" It's the Big Blue if you've had it, not the Big Red, but the Big Blue drinks. It's good. Okay. Let's go down here to the first question right here. Below is the t-test of the output and jump. Based on the hypothesis test you specified in part 1, what is the appropriate p-value? Now, if you remember, there's 3 different alternatives to a test. There's the does not equal alternative, the greater than alternative, and the less than alternative. And I'm actually saying them in the order jump puts them. We have the does not equal alternative right here, the greater than alternative, and the less than alternative. So jump shows you them in this order. If you plug in the greater than sign right here, store B greater than store A, well, if you just wrote out your alternative, let's just write it out this way. If we just, this is not our alternative, but we could write out this, and you see store A greater than store B, technically they have it flipped in the problem, so let's reverse this here. Jump puts things in reverse alphabetical order. It doesn't matter which order you put them in, but jump will always put them in reverse alphabetical order. So the way I've written this right now, with mu B greater than mu A, if we look back on this output, if we put a mu in front of this, on the jump output, to see the null and alternative, just put a mu in front of this, and it's a 2-sample test then. Mu B greater than mu A is the alternative that relates to this one. But we're not going for that. We're going for the does not equal. Now, the does not equal says that we have to take where we landed and shade to the right and then reflect it. And I should preface it with, in this instance, we shade to the right. You always shade the smaller sign that does not equal and then reflect it, because no p-value can be above 100%. If you were to land over here, shading to the right would get you more than 50%. So you always shade to the smaller side and then reflect it. So the p-value right here is actually double the smaller p-value. Notice that distinct relationship, that the greater than alternative, you see how this arrow points to the right? It's literally where we landed. This is where we landed. We landed at 7.89. This is 7.89 right here. And so you shade to the right, and that p-value doubled is the does not equals alternative. Interestingly enough, this 0.848 is the complement of the greater than alternative. Because if you shade to the right all the way and you shade to the left all the way, well, that's 100%. So the 2 one-tailed alternatives or 2 one-sided alternatives add up to 100%. You'll always get a p-value of, well, you have to think about it. You have to either get greater than this or less than this, and or basically equals it. And this red line is kind of an infinitesimally, whatever. It's very tiny, infinitesimally small. I'll try more at that later. Very, very thing that doesn't even exist. It's a hair on the planet. And so its area is not really factored into the greater or less than. Well, that's we've got our p-value there. Based on the output above, which store had a higher sample average? Well, the p-value tells us if the difference is statistically significant, which it is not. More on that later. But which store had the higher sample average? To observe that, we need to go to the output right here, and we have store B minus store A. This is the way the test is set up. So this difference we observe right here is actually the difference between store B and store A when we subtract store A from store B. So this 7.89 tells us that, when we explain it in context, that we observed that store B had a higher sample average by 7.89 more transactions than store A. That's what that difference right here is. This difference is literally solving this equation. That difference is solving this equation. Good stuff. Anything more to mention in the output? Our confidence interval contains 0, which means our test isn't significant. It's a good thing to mention there, because we're saying, well, the true difference between these stores could be 0. Think about that. We're saying that store B could do 23.07 more transactions because the difference being positive goes to store B being higher. Or we're saying that store A could do 7.29 more transactions because the difference being negative means that store A was higher. So to say we're 95% confident the true difference between store B and store A's transaction is store B doing up to 23.07 more transactions or up to store A doing 7.29 more transactions. That's our interpretation of that. And 0's in there, so could be 0. And that doesn't sound significant to me because that's our null, is that there's no difference. So what do? We fail to reject the null because we don't have evidence of a difference right here. No evidence of a difference because 0's in the interval. P-value is above 0.05. It doesn't specify an alpha. I've had people ask me on the test, what's the alpha? No reasonable person would make an alpha above 0.10. I've seen 0.10. I wouldn't use it. If you use 0.2, you're crazy. You're just like, I'm like, no, that's wrong. But yeah, you can set alpha to whatever you want, but no reasonable person, and it even has an alpha of 0.10 right there as I glance over it. So no way to reject it. We say when the P is lower than the value of alpha, we will reject the null. Okay, let's look at the next. Briefly explain why you circled the answer you did and provide numeric evidence. As we just said, if our p-value is below alpha, we reject the no. So when the p-value is below alpha, we reject the null. And no, we're not going to do that right here because our p-value, this one right here, is not below alpha. We're not going to reject the null because our results could have happened. We expected to land at 0, and we didn't land that far away. I mean, we landed a little bit, but nah, it's not that far. Okay. Your answer to part 5 above, reject or fail to reject, is not a complete conclusion for the manager's hypothesis test, although it's a start. State the remainder of the conclusion in the context of the problem. This means that we do not have evidence of a difference between the means of the two stores. There is no evidence of a difference between the true means. So store A and store B are doing, in our best estimate, the same amount of transactions. That's what we're saying right here is on average they do the same amount of transactions and we have no evidence otherwise because that was our null, that the true average transactions is the same for the stores, and we're staying with it. Good stuff. Basis of all statistical testing. I like this one right here. Type 1, type 2 error is always fun. So did you guys like that little video, the pirate video? That was fun recording. So, and then I was like, I have to include this because we have other stuff we've been doing, and we're still working. Richard's really great, and we're still working on everything else. And I wanted to make sure you guys had high quality stuff because there was kind of the thought of like, let's just put the Blackboard lectures up that I've done, and you'd be watching me like teaching other students, and you wouldn't even know them. And I was like, I'm gonna sit down. Yeah, it was fun. It was a lot of work, but we got it. We got a lot of stuff done. Okay, many consumer groups. We're just doing the test. Let's take a timestamp on this and put question 2. So I'm just going to look over at the timestamp, and we're 17 minutes in. So 17:30. So I can put links in the YouTube thing. Question 2. 2 means. This is top 1, top 2. Okay, I got my notes. Got to remember to take them. Okay, as a result, Canada's trying to approve drug process is too easy, and as a result, too many drugs are approved and later found to be unsafe. On the other hand, a number of industry lobbyists have pushed for a more lenient approval process so that pharmaceutical companies can get new drugs approved more easily and quickly. Assume that the null, and this is really the only important part so far, is that a new unapproved drug is unsafe. So we're assuming a drug is unsafe until we have evidence that the drug is safe. That's the important part of this right here. Now, we should immediately go to our paper and think about what a type 1 and type 2 error is. This is where we got to sit down and think. A type 1, as I like to say, is a false positive. You have to understand what a false positive is, though. You have to be very careful in what you think of a false positive. A false positive is whenever we run a test and we have results indicating evidence. Evidence means evidence for the alternative. It's like when you go take a drug test and you get a false positive on a drug test. Just imagine you're Mr. Clean Cut, you got you shaved, you got your hair all short, you're not all shaggy like me, and you go take your drug test and you're a clean cut person. So you should pass your drug test because you're not doing drugs. But you go in, you fail your drug test. Now this is a false positive, and it happens. It happens to like poppy seeds. I think there's a Seinfeld on that. And there is. And so it happens. There's false positives. And so they said, you don't walk in the door and they say, you're a druggie. We know it. They say we have to find evidence of this. So the null for a drug test is you're good. The null is you're good. They have to show evidence that you're not good. It's not like everyone's a druggie until proven otherwise. You're clean until proven otherwise. So with this in mind, a false positive means we found evidence. Evidence means evidence for the alternative. To say I reject the null and show evidence for the alternative, you have to have evidence. So in a type 1, false positive, 1, 2, A, B, positive, negative, and I love saying that. So type 1 is a false positive. So they find evidence for the alternative. They find evidence the drug is safe. So what does that mean? It means a new drug gets approved when they have evidence it's safe, but it's a false positive. In other words, the drug wasn't safe. So that's pretty bad. It's like, who knows how bad the drug is, but it's not safe, and we have just put an unsafe drug on the market. Type 2 error is a false negative. This means that you're actually a druggie when you go in there, and they're like, hey, you're good, which is like everyone's dream, not mine, but like all these people, apparently. It's like, oh, man, I just passed my drug test. And it's like, I pass them all the time. Just give me one right now. It's just like, anyways. But with that in mind, a type 2 error is a false negative. So they don't come back with any sort of results. They don't come back with anything of interest. It's like, yeah, well, we're gonna continue to believe the null. So the null is that the drug is unsafe. They wanted to find evidence that it was safe, and they didn't find evidence it was safe. But it's true, it's safe. In a false negative, we should have rejected the null because it's a false negative. We should have had evidence. So in this instance, a safe drug does not go on the market. We had a safe drug and it didn't go on the market, so that's bad. A consumer, this is which type of areas are the consumer groups. So if this is a consumer group that is trying to protect consumers, they'll be more concerned about a type 1 error where we say the drug is safe. Remember, a false positive is we have evidence it's safe. So the consumer group would be very concerned about putting an unsafe drug on the market. We asked patient, I think we had another version of this problem that said which one would patients be more concerned about. If you were a patient, you'd be more concerned about probably a type 2 error where you didn't get a life-saving drug. So type 1, type 2 error is all contextual. One is never always worse, never always. It's just contextual to whatever situation you're in. So, and to who you are. Okay, we're back to, let me get the timestamp on this. We're back to 2 sample T's. Didn't we just do one? Well, that didn't take too long. 2140, 2 sample T's. Okay. So with this in mind, below is some output for a 2 sample t-test. Assume the necessary conditions have been met for the t-test to be valid. And that is randomization, 10%, nearly normal, and the independent means condition. Important to know what we're analyzing here. We have standing versus sitting. What are we analyzing? The difference between means of standing and sitting. Does it say what we're analyzing? The represents a 95% confidence interval. Who knows? We gave people their exam when they were standing or sitting. Sure. I don't know. It doesn't say what the data is. I don't think it does. So it's just 2 groups. We can look at it once again up here because who knows what we're going to ask. So sometimes we can just think about what could come from this. The difference right here is the difference between standing and sitting. Standing has a higher mean than sitting by about 1. The standard error of the difference is the formula S. I might just show it off here. Standard error, it's S sub 1 squared over N plus S sub 2 squared over N sub 2 square root. Let's go right here and go to Google, our good friend Google, and go to standard error of the differences. And we can just view it. Oh, that's for a z-test right there, so let's not view that. And they're giving a bunch of weird ways of viewing it right here. Hello! Are we going to see one that looks like ours? Let's type in this. Let's type in 2 sample t-test formula. A 2 sample t-test formula. Here we go. There it is right there, and there's the standard error of the differences right there. S sub 1 squared over N sub 1 plus S sub 2 squared over N sub 2, square root of it all. And it looks like our S over square root of N, just S over square root of N has been squared, and we're adding together 2 of them. So that is what we have going on. If you've heard me say this many times, a test is always an observed difference, or excuse me, a test is always an observed minus expected, which makes a difference. Here's our observed difference between the sample means. Here's our hypothesized difference, which is often 0 for this test. Don't worry too much about the formulas, but you should know how to use them a little bit. I like the theory behind them because we always standardize a difference to get a test statistic. Speaking of standardizing that difference to get a test statistic, the t-ratio has gone missing. And that formula comes into use right here. Because if we take a difference and we standardize it, we get the t-ratio. Do you guys see it? Do you guys see how to get the test statistic? You take a difference and you standardize it. I think I did this in the video. I think I put it in. I think I drew it in. I think I edited the video. Do you guys remember it? Yes, no, thumbs up? No. It's all right if not. What you got to do is you just got to divide this out. Literally divide it out. Here's the new calculator for Windows 10. Windows 10, everybody. Give it a round of applause. It's all bigger and Mac-y. Everything looks like a Mac on a Windows 10. So I like the new calculator. And this is going to give us about ones, like 1.04. What's going to be? Oh, it's higher than that. 1.15. Because, and if you look, now this over here on the right is not showing us 1.15. It's actually showing us 1.089, but the standard errors are basically 1. And the standard error is what we standardize by. So it almost looks like a normal curve. I mean, it looks very similar to that. So, you know, good stuff. We can just divide the difference by the standard error of the differences to get the test statistic. Excellent stuff. That is the answer to this question right here. The values for the 95% confidence interval have also been erased. Now, this one blew people's minds. This one people just, they went crazy over. And I have a great way of solving this. There's something we should realize. This T-curve, and if anyone wants to say anything, like this T-curve is basically, just think about it for a moment. We talk about this a lot in the in-class section. This T-curve is basically normal. Now, someone would freak out on me. Statisticians would be like, no, it's a T with 43.89 degrees of freedom. But remember, Mr. T comes in and he says, I'll pay the full. Did I do that in the online class? I don't think I did. Did I? It doesn't work that well in the videos. No, I think I did do it in the videos. I can't remember. But the T-curve is smashed down. The T is like smashed down. It's a smashed down normal. And it becomes more normal with more degrees of freedom. I think I did show it in the online videos. I think I did. And then what we have here is basically a normal if you just look at it. So what is a 95% confidence interval z-score for a normal? And this is not the correct answer. It's actually a T with 43.89 degrees of freedom, but it's almost 2. Now I want you to think about this. Since it's almost 2, the T-score, because a confidence interval, let's look at the formula. Confidence interval to sample mean. Here we go. And there's our good friend, the standard error once again on the right. That's the standard error. So it's just the difference plus or minus the T statistics times the standard error. The standard error, you guys hold up a finger and tell me what's going on. The standard error is basically what? Standard error is basically what? It's basically 1. And the T-score, I love it, Brenda, thank you. The T-score is basically 2. Exactly. So think about this. The margin of error is basically what? 2. Margin of error is basically there you go. Margin of error is basically 2 because it's 1 times 2. And the standard error here is 2. This whole formula right here, the standard error of the differences, is what we get in the jump output right here. We're not square rooting that. We don't put 2 in here and square root it. It's that whole thing is the standard error of the differences. Like even under the square, like the square root, blah, 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 is the standard error of the differences. So 2 times 1 is 2. So the margin of error is 2. So if you take a look at this, you have a difference of basically 1. So you add 2 to 1, you get 3, and you subtract it, and you get -1. And we scroll down here to our answers. And the only answer that makes sense right here is this one. This other one could technically be really close to it. This answer is close-ish, but it's not the right answer. If you were to solve out the center of this interval, the center of this interval wouldn't work out. If you do if you do max minus min of an interval and divide by 2, you'll get the center. So 1.08 should be at the center of this interval, which it is, the one I'm highlighting. 1.089 is at the center of that interval. That's the way you could test some of these other intervals. They don't have the right center, so they can't be the right interval. So a lot of people found this problem to be extremely challenging. Frankly, maybe it'll make a return on the test. Everyone's like, how do I do this problem? And I'm like, there's a lot of ways. It's a great problem. There's a lot of ways to solve it, and that's the hallmark of a good problem. I like my way where you kind of just create the interval, the T statistic for the interval, because remember, 95% confidence interval for a Z is basically 2. I know it's 1.96. It's like 1.959, yada, yada, yada. For those who say, oh, Brian, you don't know it. I do. I promise I do. It's like 1.959 I think it's a little more extended out. We basically round it to 1.96. So there it is. Oh, break my glass. Okay, so let's continue on from that fun excursion. That's it for that problem? Oh, I like that problem. Okay, let's get the timestamp on this. If there's any questions, you can feel free to ask. I'm going to timestamp this problem. 30. That's where my neighbor's probably going to knock on my door. It's going to happen right now. It's like, he'll knock now. He'll be like, Brian, what are you in there doing? I'm doing a review. So, okay, this looks like proportions to me. So let's write down proportions right here. It's amazing just by glancing at a problem what you can notice. What I noticed was, oh, no, I'm way wrong. It's amazing what you can notice when you're wrong. It's a one sample mean. And I know that because I saw decimals. As soon as I saw the decimals on year, I was like, this is a one sample mean. So just be careful. There's not two samples here. And I think Thiel thought originally this might be a two sample mean because we said like compare it to something. And people are like, wait, there's two samples. No. You've only got summary statistics for one. So let's start jotting down what we got for this problem. Okay, so we have a sample of 100 policies. That is n equals 100 policies. We have that the policy, the average lifespan, which is x bar or y bar, whatever you choose. It's just the mean of variable, whatever you want to call it, mean of variable x, mean of variable y, is 78.32. We also have mu naught. So I'm going to call this mu naught over here in just my quick side notes. That's the little mu curly thing, just so everyone can see if you fast forward to this part of the video. Mu naught is that, and I tell you what, let's do this all professional-like. If I can get it. There we go. Let's bring this in over here. So let's put in the right symbols. You know, never hurts to do it right. No, you go back to your size. There we go. So we already got a mu, and it's easy enough to put back in. So we have n equals, no, I want little n, not population n. And then x bar, well, those things are tiny. It's going to be much easier to write x bar. And yeah, it's going to be hard to get a mu on here because I got to expand it again. Insert, symbols, symbol. And maybe I'll show you guys. There's a lot of neat things you can do. This isn't a Microsoft Word class, but if you want to, you can always put in, I had the hardest time doing things like x bar for a while. Insert, symbols, equation, design. Yeah, we're going to need to full screen this. Design. And then we need to go into, I know where it's at. Give me a second. Accent. And where's my bar? There we go. So that's how we get an X bar right there. And it's in the center of the screen. I just know how to, boop. There we go. Now we got an X bar. Everything looks right in the world now. That's nice little touches you can do. 78.32. Okay. Do things right. That's the way I say. Even if you're writing out symbols. And that's the big thing is these symbols are so important. I'm kind of glad I stressed that for a second there because you need to write these down properly. You need to know what you're putting into your equations, what you're doing. Because if you write the wrong thing, everything just blows up. There's one other thing we should be missing here, and that's standard deviation. Standard deviation. Why is it little tiny standard deviation? You can be big like the rest of your friends. There you go. And that is 4.2729. There's our standard deviation right there. So we have all of our notes on notation, and we're excellent. Assume that the conditions to perform a hypothesis test are met. Oh, man, it's no fun. Come on, I can give the conditions. It's random. We randomly selected these policyholders. 10%, less than 10% of all policyholders. And that the distribution is nearly normal. Since we have 100 samples, it doesn't say anything about the distribution being like ridiculously skewed. If it was ridiculously skewed, we'd have a problem with the nearly normal condition, but no, we're good. It's 100, and I don't see any inclination of problems. So we seem to be good. Let's go ahead and write our null over here on the side. Our null is going to be stated that the true mean is equal to the hypothesized mean. That's all we know so far. The null states that the true mean is equal to the hypothesized mean because we have a null value. Technically, this null value right here is mu equals mu naught, and mu naught is 77. You can see that on your calculator too. Let's go ahead and copy paste and then figure out what we need to do with this to get the alternative. Looks so nice on the screen. I like it back down a little further. So the alternative now, the alternative hypothesis, is going to be some sort of other sign in here. And let's see what they're asking. They're asking, the company will change its premium structure if there is evidence that people who buy their policy are living longer on average than before. So the true mean is, say it all with me, greater than. The true mean is greater than 77 if they're living longer, because this is what they're testing. They know that their policyholders in past have lived 77 years. They want to see if they're living longer than that on average. I need more tea in a moment. I'm just drinking water now. So with that in mind, calculate the appropriate test statistic. This test statistic right here comes from a one-sample t-test. Doing your notation leads you down the proper pathway to solve the problem. Write the notation, and then you'll know what formula to use. You can do this on the calculator under t-test. So let's bring up t-test formula. Much easier to Google these things and just view them here. I like it. Those are all two-sample t-tests. Those are not the right thing we're looking for. Show me a one-sample t-test. Don't write it all crazy like. That one's nice enough. So we have, and they don't have mu naught. I wish they did. Why don't they write things the right way? People get lazy. Says the guy looking up stuff on Google. Hey, my buddy. What's up? There we go. So once again, we have an observed mean minus an expected mean. This is the expected mean according to the null, where we should land. And then we have a standardization factor on the bottom, which it's not just S, it's S over the square root of n, which is the standard error for the mean. So we have observed minus expected over standard error of the mean. So this is our standardizing factor, which has been set for the sample size. And now it's a standard error because it's an estimate where we are using the standard deviation. We're not using a standard deviation of a population here. So let me re-speak. This is from a sample, so it's a standard error. It's from a sample, it's not from a population. We're not using sigma, we are using S. Sigma is population standard deviation, where S is sample standard deviation, and we're using that to talk about the standard error of the distribution of means for this sample. Okay. So with our notation on the side, let's bring up Word, and let's bring up the calculator. So we'll put it over here. We don't really need to read the problem right now. So we need to do x bar minus mu naught, which that's an easy enough formula right there. And now the amazing thing about this is the bottom part, which is S over the square root of n. Square root of 10, just show me on your hands, what's the square root of 10? Square root of 10 is what? I mean, 100. I'm saying the answer. Yeah, it's S over the square root of n, and n was 100. So we're dividing this by 10, which means we move the decimal. All we're doing is moving the decimal. So this is the standard error of the mean. The standard error of the mean is the standard deviation divided by the square root of 100. Square root of 100 is 10. And now we get the test statistic t. So our t is 3.089. So this is our t right here. This is our test statistic. That is our standardized difference. Down here at the bottom, circle the appropriate p-value. This was a greater than test, so we need to do probability greater than. Remember, the way we set up our alternatives is the way it's going to point. You see how this one right here points this way and this one right here points this way? That's the right alternative. So we're shading to the right, which is an area we can barely see. Now think about back to the normal rule. This is a t with 99 degrees of freedom. A t with 99 degrees of freedom. So it's basically a z again. It's basically a z. I know it's not a z. I'm just afraid a statistician's going to watch this later and you're telling them there's no difference. The differences are most pronounced when we have small sample sizes. That's why William Gossett made it. But we can think of this as a z just for our own mental purposes. And when we have a z of basically 3, we have 99.7 in the center, which leaves 0.3 on the outside. And one of my hands, if 0.3 is on the outside, is 0.15. And look at what our answer is. 0.0013 instead of 0.0015. We didn't get an exact t statistic of 3, and this is a t, not a z, but our answer is still in the same idea of 99.7 in the middle, 0.3 on the outside, 0.15 in one hand. That is 0.13%, and we could have estimated it at about, it's about 0.15. So once again, the Z gives us a good idea, and that's why the empirical rule is so important. It's like, boom, it's mind blown. So with this in mind, do we reject? Most definitely. There is tons of evidence here. This is very strong evidence. This is most importantly to say statistically significant evidence at the 0.05 alpha level, because our p-value is below that. Our p-value is below 0.05. We have a p-value of 0.0013, and we have statistically significant evidence to say that our policyholders are older than 77, that we reject 77. We have evidence that the true mean age of our policyholder is above 77. Okay, fun stuff. If you have any questions, feel free to ask. I'm going to keep time stamping. Just, you can turn your mind and be like, hey, Brian. So I'm going to grab some drink here. Let me write down 4130. I'll probably tell one.
Hey, Brian.
Drink real quick if you want.
Can you hear me?
I'm back. My kitchen's right back there. Okay, okay.
Can you hear me, Brian?
There's my paper.
No.
Okay. Next problem. A UT student decides to analyze the relationship between Greek life and family economic level. Automatically, those two questions right there, and hey, if you did the project, you might have seen this data. Boom. Think about it. Greek life and family economic level. That should tell you what analysis we're doing right there. Both of those variables are, hold up your hand if you want, show me what they are. Just the first letter. They're both what? Both variables are categorical. They're both, exactly. You're like, how do I hold up my hand and say it? Like, see, it's own new sign language. I cannot. But they're both categorical variables. So this is chapter 22. So let me write that down. This is chi-squared. This is a chi-squared problem right here, and it's chapter 22 or module 20 for the online class. I should try to make sure I say what modules it is, but it is chi-squared. State the null and alternative. Yay! For this one, we get to do some fun stuff. There's so many ways to say this. Statisticians have a way they like. It's whatever. Statisticians kind of like to say, because it's a chi-square test of independence, so they're like, oh, the proper way to say it is that Greek life is independent of, and what's the other one? Economic level. Greek life is independent of economic level. Greek life is not independent of economic level. That's fine. I like to say there's no association between Greek life and economic level. There's no association. The two are, independent. That's what it means. There's no association. The alternative being that there is an association between Greek life and economic level, because we have to show that. We have to show that these two things have an association. Association is a great word because it encompasses correlation, because correlation is its own thing with quantitative variables. And everyone likes to say these two are correlated. No. That's quantitative stuff. That's why we have quantitative for correlation. So watch the words. Association is a good one. Correlation is a specific one. It is hot in my apartment. Tonight's a hot night. So there's the null and alternative for that test. Use the contingency table on the next for the solve for the three missing values. Let's scroll down here. Okay, we have a count that is missing. This count right here is going to be the row total for no, and we could subtract out the two values. And as long as I do my math right, I should get the right answer. So that count right there is 225, and you can double check your math by adding it to 208 and see if you get 433, and you will. Now we get to the slightly more complicated stuff, but there's tricks. The expected cell count right here is missing. But check this out. The expected cell counts have to add up to the total. A lot of people don't realize that. So if I take 110, the total there, and subtract out the expected cell count here, 41.0356, I get the expected cell count for this, because it has to equal 110. Those two added up together. we can check our formula way of doing it of row total times column total over grand total. So we got like 69 point something, row total, it's column total technically, times the other one, and then divide by 898, we should get 69 point, and that's what we got, right? 68, it was 69 basically, that's the same answer. So that was row total times row total times column total over grand total. You just line them up. Row total times column total over grand total, line them up like that. The last one, the cell chi-squared. The cell chi-squared tells us how odd something is. It's the difference between the observed and the expected squared, because if we don't square it, we'll get just 0 if we add them all up, because they'll just negate each other. And then we divide by expected to standardize it. So with this in mind right here, we observed 110 and we expected 132. That's a difference of about 22. 22 squared is about 500-ish. 132 dividing by that's like 3.8. Let's see what we get. So we take observed of 110. I'm just doing the observed right here. That's the count. Minus expected. And then when we square it, it becomes positive. I said this is about 500. Hey! And then I said it's going to be about 3.6-ish. Yeah, 3.6, I guess. And then divide by the expected. That was off. Close-ish. But, and I want to stress this. I hope no one time a student was like, or they wrote in a review, they were like, always trying to show off that he knows how to do math. But someone wrote that. I'm not trying to show off. What I'm trying to do every time I do the math in my head is I do it for my own benefit because I want to make sure I'm doing it right. And I can come up with good enough estimates of what the answers should be. And if I can estimate what the answer should be, if I punch it into the calculator wrong, like if I just hit one wrong button, everything blows up on the calculator. So I always estimate it in my head before doing it to see if I'm right on the calculator. So it's just kind of a good mental thing, I think, to do, just kind of guesstimate and get good guesses on stuff. And if I had gotten like 6 or 7, I would kind of rethink the problem for a moment. And that's happened on the calculator. And then sometimes I just did it totally wrong in my head, so that happens too. But it's always good to estimate and kind of give yourself a little math practice. And you just get better and faster as you keep doing it. Every time I punch something into the calculator now, I solve it in my head first. No matter, there's problems that are too big for me to solve in my head, but I really don't solve those much. Degrees of freedom. This is the fun and easy part. This is a 2x3. This is a 2x3. A 2x3 turns into a 1x2. This has 2 degrees of freedom. There's 2, and don't count. I almost did this today in class. Brittany, you're in the class today, right?
Mm-hmm. Yeah.
And I almost messed it up in class today. I think I got my sound off. Now I got my sound on. I'm gonna have to turn it off. So I almost messed it up in class today. A student said the right answer, and I was like, no. And then another student said the answer I had, and I like paused, and I was like, wait, you were right. So I make mistakes too. It happens. I caught up in the mistake a lot of students make. This is a 2x3. You do not count the totals. 2x3 turns into a 1x2. This is the inner portion of it. It has 2 degrees of freedom. The Pearson chi-squared test statistic. Let's solve it. Well, we already have one chi-squared right here. We need to add up this one right here. I am adding all the chi-squareds in the cells. I am adding all the cell chi-squareds. I am adding all the cell chi-squareds. And you usually get something close to likelihood ratio. Close-ish. If you were to get something crazy different, you probably did something wrong. But we use the Pearson for the p-value. Very important note right there. The Pearson is your p-value, rather the one associated with the Pearson chi-squared test statistic. The chi-squared test statistic is the sum of all the cell chi-squareds. The cell chi-squareds indicate how odd an individual cell is. Meanwhile, the Pearson tells us how odd all the cells are, because it's all the cell chi-squareds. So in a chi-squared curve, which I do not know if we show on this problem. So in a chi-squared curve, let's go to chi-squared output. Stat distributions chi-square. Do I have it? I got it. Here we go. We had 2 degrees of freedom. We need to put in our. Can you guys see where this curve even ends at? Look at This is what we would call the critical value, which we don't use much. Any chi-squared above this is reject the null. So we landed way over here at like 49. I need to even really do this. Our chi-squared is this, and it's p-value of 0, which when we look at the output over here, all that. Wait, it's the other web page. That's where it is. Looking at the output, it doesn't even, if we were to hover over this and jump to look at the p-value, which we can't do here because it's not a static output, we would say basically 0. It'd be like e to the negative 500 or something like that. So yeah, that's a very small p-value. A really cool thing about the chi-squared that I love, we always say degrees of freedom to be normal, and that holds true for a lot of these distributions. The F is a weird one. Let's just not talk about it. Pretend it doesn't exist. But the chi-squared, as we increase the degrees of freedom, do you guys see it becoming more normal? Put to 10 and then put to 100. I mean, it becomes more normal as you give it degrees of freedom. The center of it will be the degrees of freedom. So that becomes more and more true. If I put it to like 300, it'll be even more normal. And it apparently can't display that. Probably only display up to 200 or something. I don't know why this didn't design their applet that way. But yeah, and now this would fall over there. But you don't need to know that. I'm going to, the in-class section, I want them to know that a little bit. I'm probably going to make a bonus question for them. We just went on a tangent in class that I think is important to learning. It's kind of a cool concept. But online class, don't worry so much. It's kind of an interesting fact. And that wasn't in your guys' module, so in no way I could include that. Maybe I'll make it like a 1-point bonus. Who knows? It'd be bonus if anything. So don't be like, I need to study the chi-squared for an hour. No, don't do that. Okay. Use the output on the previous page and one of your values you calculate to calculate the chi-squared test statistic. So we did that. It was there for us to solve. So I was just like, well, I'll solve it. It's blank. State your conclusion in context of the problem. Our p-value is below 0.05. So we reject the null and we show evidence that there is an association between family economic level and, was it Greek life? Family economic level and Greek life, yeah. There's evidence of a relationship between those two. Use the mosaic plot to help describe the nature of the association. It's what we would think. This is real data. It's people in Greek life are more likely to come from upper class, and that people not in Greek life there's greater portions in the middle and the lower class. It's not to say, oh, you're in Greek life, you must be rich. No, there's people in Greek life who report not being so well off. Oh, you're not in Greek life, you must be poor. No. I mean, a lot of UT, we go to a college, so a lot of UT has a decent amount of money. So I always like to stress the point that statistics it's not about stereotypes. It's about trends in data, and not everything follows the trend. It's just a trend in the data. We generally see that people in Greek life have more money. That's what we generally see. It's just a fact. But does it describe 100% of the variation? No. It only describes 3% of the variation. 3% of the variation in your family's economic level is explained by Greek life. That means there's a lot of other things that explain it. It's like, and that's why you're like, oh, this is significant in explaining it. It only explains 3%. I had a lot of people being like, my R squared's really low. And I'm like, well, I mean, on the project, it didn't need to be significant. But, explain to me if it is significant or not. And this is a significant R squared because the p-value is low. R squared in and of itself is not significant. I might just put that on the test. R squared can't be significant. It is significant. Excuse me. It is significant if the p-value is significant. So this is a significant R squared because of the p-value, not because of R squared. R squared could be 0.97 and not be significant. R squared can be 1. If you put 2 points up, a line will explain 100% of the variation. But statistics are configured in such a way that that's not statistically significant because we know that happens. We're like, well, no duh. 2 points can be explained by a line. That's not a significant relationship. So statistics would give that an insignificant p-value. So we have buffered ourselves against the naysayers. Okay. Brian's all ready to take on the battle of statistics. Let's do question number 6. I went to the wrong button. Oh, there might have been a chat question. Oh, did I do that, Brenda? I did? Okay, cool. I didn't see the chat question up there till right now. That's all right. 55 minutes in, we're on this question right here. Let's take a look at this question right here. This is a question. It's about time we did some proportions, right? This is proportions. So let's write down proportions right here. My pen is dying. I'm writing this on a list of Xbox One games coming out. Bunch of good games. Okay, so enough about video games. So with this in mind, I'm dropping my pen. 2 seconds, everybody. Okay, so we have here that a laboratory purchased 190 seafood items, and they randomly selected them, 3 states, yada, yada, yada. 22.1% of the packages were mislabeled. Notation. Let's bring up our word notation. Okay, here we are. Notation, notation, notation. They bought 190 seafood packages, and this is where people get really confused because what we have here with 22.1 is specific, and we'll label it even properly using our fun word abouts. We're going to go to insert. Where's my equation button? Did they take it away from me? Insert equation, and let's put it in under design and go to right here. And where is my little hat? There it is right here, I think. There it is. This is P hat. Very important to do the notation properly. This is the sample proportion they observed that were mislabeled. The sample proportion they observed that were mislabeled is equal to 0.221. So specifically right here, we can find out if we take the number they took and then we times it by the proportion missampled, we can get the amount. And my guess is that we were going for 42 at this problem. I mean, that's so close that I don't think we were not going for that. So let's go ahead and punch in 42 right here as the, this is the observed amount. So just so you can see, x over n is equal to, if we take x and divide by n, that's equal to the sample proportion. That's equal to 0.221. So I just times the proportion. It's like 22.1% of the packages are mislabeled out of 190. Well, how many were mislabeled? 22.1%. So you times it by 190. That's all I did. You times this by 190, and you get 42. And that's where I got x equals 42. So we've written out the proper notation here, which is just, I can't stress how important this is to this problem. Notation, 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 because it's easy to see that it's proportions now. We're using sample proportions to probably do some confidence interval. Yeah, this one does a confidence interval, I think. Probably do a test. You can do a test with your confidence interval. Condition 1, Condition 1, random. Condition 1 is random, so we have to randomly select these, and I think this problem says here they were randomly selected. Condition 2, 10%. Unless you think that there's only 1,000 seafood packages in these 3 states, I think we're good. So reasonable people would believe that we have sampled less than 10% of the population of seafood packages that exist. Condition 3 is the success failure condition, which it states we're going to make a confidence interval. So a confidence interval is based off of the success failure condition. Oh, these are the crazy test questions I was thinking of writing. A confidence interval is going to be based off NP hat, and this needs to be greater than 10, and NQ hat. Can I change just that? No. NQ hat. Now, it's very important that the hat's on it. I actually don't say that with sarcasm. I say that in very much seriousness. Because our confidence interval is based off of this. So let's put its little hat there and make it happy. You know, Pharrell's got something going when you say a word like happy, and you just got to think of someone like Pharrell. Like, man, you own that word now. That's a good word to own. So there is our condition right here that NP hat and NQ hat are greater than 10. And we meet that because this says we need to see this many successes. We have 42 successes. So in a success being a mislabeled package, which means our number of failures, so we could write successes equals 42. Got something lit up there. And failures, nope, nothing lit up. Successes misspelled. Oh, just not capitalized. Failures is going to equal 148. And that's what this means right here is the number of sample successes and the number of sample failures. So because it's in a sample as p hat. So we're good on that. We meet the conditions. We are good. And that's how we would check the math. How many seafood packages were mislabeled? 42. Compute the standard error. The standard error is p hat times q hat over n square root. And this is for a confidence interval. So with a confidence interval, we need to do p hat times q hat over n square root. Let's look at it. Let's just look at the formula. Good stuff looking at formulas. So here's our formula right here. This inside the formula is q hat. What I'm circling right here is q hat. It's just the complement of p. So p hat times q hat over n square root. This just stands for whatever z we're using. It stands for the confidence level. This is all subnotation right here. Not everyone includes that. We usually write it this way, stating that you can pick the z. We need the z for whatever degree of confidence we need. So the formula right here, it was 0.221 times, and we need the complement of that. It's 0.779. I think that's correct. Please start yelling at me if it's not. That's correct, is it? I think it is. And then let's divide by 190, and then let's square root it. And I've done this problem before, and that looks to be accurate. 0.221, 0.779, that's right. Good. And so we have everything proper right here, and I square root it. A lot of people forget to square root it. If your problem starts turning out all crazy, then you know you have a problem. This is the standard error for the confidence interval, which we're looking at right here. We're good. Let's go down. Construct a 95% confidence interval. I mean, z is basically 2. The easiest way to solve this right here is, you see, we already got this in the calculator. If you look at it, all you're doing after you solve for the standard error, which is this portion right here, is you're just timesing it by 1.96. And this is now the margin of error. It's no longer a standard error. When you multiply it by z, it's a margin of error, because margin of error is everything after the plus or minus. So this is the exact answer right here. And then we need to copy it, because we're going to take 0.221 and add to it the margin of error. So basically 28%. And then we're going to take 0.221 and subtract from it. We're going to do the plus or minus. So 16.2 to about 28% is the answer. If you do in your calculator using the one prop z interval, you will get that same answer with the notation right there. One prop z interval is the correct thing in the calculator. It's like number something. Like number 0, I think. Could be right on that. Or it's number A. It's one of those later ones. Intervals come later on the calculator. Okay, more questions. Interpret your confidence interval. I am 95% confident the true proportion of, and that's key. Let's slow it down a little bit. Confidence intervals have a very specific interpretation. I was about to just yell it out, but let's make sure you guys know this. I'm going to mess up my little word notation thing over here, but every confidence interval is going to have the interpretation, I am blank % confident that the really word, just make it that size. Go. New Windows has smaller areas to grab, I feel. Okay, there we go. That the blank, and I can't stress this one enough, is contained that second part right there is a big portion of the problem. I am 95% confident that the, pause for it, true proportion of mislabeled seafood packages in these 3 states. And that's about as best as I could do, because that's what we sampled. We sampled seafood packages from these 3 states. The true proportion of mislabeled seafood packages from these 3 states. Remember, I'm saying the true proportion, the actual proportion for all seafood packages, is contained in the interval 16.2 to 28, I believe it was. So then you state the interval. Confidence interpretation has 3 parts. It doesn't fall within the interval. It's that the interval might contain it. Because there's a true proportion that exists. There's a bunch of seafood packages, and there's a bunch that are mislabeled. And so the true proportion exists that are mislabeled. So we're trying to make a confidence interval to contain it. The confidence interval is the active thing because we're making the confidence interval from a sample. The true proportion is just what exists. And our confidence interval might contain it. That true proportion doesn't move. It doesn't fall anywhere. I hate it when people say fall. When I was in step 1, I was like, what? It could fall inside there. No. It exists. And our interval might contain it. Our interval might contain it, or interval might not contain it. That's what's going on right here. It doesn't go, oh, I'm going to jump inside your interval. It's like, did the interval get it or not? That's what's going on right here. So good stuff. A bunch of wording, a bunch of stat nerds. That's me. Okay. Let's bring over our little notepad thing to the side. Windows 10, why you do me like this with these little small, hard to grab things. Look at that. You miss it for a second. Okay, bring back to our notation on the side. Interpret your confidence interval. We did that excellently. What we got next? Problem number 7. Let's take the stopwatch. See where we're at. We're at 1 hour mark. Yeah. Problem number 7. Okay, that was on confidence intervals, proportions. And problem number 7 is at 1 hour and 7 minutes. My pen is dying more and more. Okay, 1 hour, 6 minutes. Okay. What is this problem going to be on? An insurance company checks the police records of 582 accidents in the state of Tennessee, selected at random, probably a condition, and notes that teenagers were at the wheel in 91 of them. What are they answering here? They're answering the question, was a teenager at the wheel or was a teenager not at the wheel? This is a categorical response. You can't get the mean of teenagers at the wheel. It's not a number. So this is a categorical response right here. We know that we observed. So what do we do when we have a problem? This is the best way to solve them. Immediately you get a problem. I don't even care what this problem says right now. And I do, but I don't. We go over here to our little notation thing. We write down n, and it does that to us for the 50th time. N equals 582. And then we have x this time. And then we can get p hat, which is going to be the sample proportion. And there's our sample proportion right here, 15.64. We go here and insert equation. I know it might seem crazy that I'm doing this for each one, but I can't stress the importance of using the right symbols. I don't want to just write down some craziness. Symbols. And watch me get one wrong. Feel free to point it out and email me. I'll be like, give you a point or something. Now people are going to email all these crazy things. It's 0.1564. Okay, that is the sample proportion. I mean, you can resize the calculator now? That's kind of neat. Guess it makes sense. Okay, so here we are. State the null and the alternative. Well, what were they trying to think about in this problem? The company sets insurance premiums based on percent of teenagers' accidents. The company executive decided to have higher premiums in the state and called for tighter restrictions, they claim in at least 1 of every 6 accidents to teenagers behind the wheel. Is the data consistent with the executive's claim? Answer this with a hypothesis test. So they say there's evidence. So you're trying to see if there is evidence that there is a teenager at the wheel in at least 1 out of every 6. So let's see if that's true. Let's go ahead and assume that 1/6 is true and set that to our null. So our null here is going to be that the true proportion of accidents where teenagers are at the wheel, which is going to be P, is equal to 1/6. 1/6 is point. Expand the window a little bit. 1/6 right there. It rounds that. The alternative will be, and let's put the alternative. Do we have evidence to support the claim? And it is that P is greater than. So he says in at least 1 out of every 6 accidents. So in at least. So we're going to say, oh, so you have evidence that in at least, this is what he says he has evidence of, that at least The true proportion of accidents is at least 1 out of every 6, which is greater than 1 out of every 6. Compute the appropriate test statistic. This is a 1-prop z-test now. A 1-prop z-test, go away. Thank you. I don't know if you guys can see that. One direction. 1 proportion z-test. And here we go right here. That's the conference rules. Is that a big enough? Here's a big enough one to see. Here we go. So this right here, if we were to check the conditions, is actually based on P0. P0 is the null proportion. So I actually didn't write that down in my notation. Shame on me. I should have written down here P0 is the null proportion, which is 1/6, and you don't change my thinking. So P0 is 1/6. So that's important to note right here. P0 is 1/6.
Hey, Brian, where's that?
And that's why we're testing 1/6 as a value. So if we were to do the conditions, the success failure would be based on NP0. And we would definitely pass it. NP0, 582 times point, that's fine. And then if we did it by the complement, times 0. That's NQ0 is fine. So we're good. So let's do the test over here because we checked the conditions out. So we need to take the sample proportion. Can I get it all on the screen at once? I'm going to scoot stuff. There we go. I need to take the sample proportion, as I said, which is the observed minus the expected over the standardizing factor. In truth, it's easy to solve the standardizing factor first at the bottom. When you solve these, take your P0 and Q0. That's P0 and Q0 because Q0 is 1 minus P0. That's what Q0 is. And then divide by your sample size and then square root it. And that is your standard error. Be careful with these e's to the negative yada yada yadas. They're numbers with decimals. They're not 2 point something. It has 3 zeros on it. So that's why when I square rooted it, I went back to the zeros. So now I'm going to take this right here and copy it for a moment. I just copied it. It's in my copy. Then I'm going to take the observed sample proportion of 1.564, and I am going to subtract from it 0.1667. I am now solving the top of the equation right here. And now I'm going to standardize it. That is literally the top of the equation right there divided by the bottom of the equation. And we get negative 0.66675. And that's actually a fascinating number if my p-value calculations are right, because I don't know if we get to see the p-value for this test, but you should be able to draw a normal curve from this. And with the normal curve, you're shading to the right. This p-value is huge, and it confused people because you're on the left side of the curve and you're shading to the right. You see our arrow shading to the right. When we go to the normal curve right here, let's go over to stat distributions normal curve. They got a nice one. Sorry, David M. Lane. Sure, that'll work. Oh no, I typed it in too crazy. David M. Lane. He's like, no, can't get away from me. Okay, sorry, man. I apologize. So let's go above, and here's the interesting thing. I can almost tell you exactly what this is going to be for the p-value. This is actually the interquartile ranges z-score, and I think the p-value is going to be right at about 75%. Yep, right there, about 75%. Because the interquartile range, I think, is 0.67. Negative and positive 0.67 is 50% inside. So knowing that, I was able to actually compute the p-value. But still, I mean, over from 0, can you guys tell me the p-value if we landed at 0 and shaded to the right? What would the p-value be? I think you guys know it. It'd be 50%. If we landed right here and shaded to the right, it'd be 84%. So the empirical rule comes back into play that the p-value must be above 50 and less than 84. And as you see down here on the answer, that's what holds to be true. And using extra stuff that I know, I was able to get closer, but I don't expect that from you guys. But I would expect you to know how to draw this. So drawing this out, nice and easy. Based on your hypothesis test, in part, which screenshot on the next page shows and here's the thing. I can't say this enough. You should be able to you should draw these before even looking at them. This is the way I do my problems when I solve them. I don't even look at the answers because I already know what I should look for. The answers I should look for, is really only this one right here. And there's the answer. And you know what drives me nuts? That's not the exact answer. I remember this problem. It drives me nuts. And it's all right. I'm not the best test writer in the world, so if any of my colleagues see this, I'm not mad. But if you solve it in the TI calculator, you'll get very close to what I got. But this answer right here is off by a little bit. But still, no one would know that unless they were solving it. But this over here is a T-curve. It has degrees of freedom, so it's a T-curve. So this isn't the answer. We're only using the T-curve for the means. And funny enough, if you just do process of elimination, it's like these two look alike and these three look alike. So then it must be this one. It is. But that's because it's a normal curve, and yes, it looks good. Interpret the p-value from your circled area image. It means the probability of our results or results more extreme according to the null hypothesis being true would occur due to random chance variation about 75% of the time. So the null is probably true because our results are in line with what we would expect with the null. And so we do not have evidence that more than 1/6 of wrecks are caused by teenagers or they were at the wheel. State your decision and make sure your answer's in context. There's no evidence to go with this buffoon's claim. The guy's a jerk. That's what I'd say. We do not reject the null. The null said that it is equal to 1/6, so we have no evidence to go against that. We do not have evidence that there is teenagers at the wheel in more than 1/6 of accidents on the road. We do not have evidence for that. What do we got? True false time. Woo! Let's write down what that last problem was. So that was proportion test. Where are we at on the time? Let's do some true false. True false. Okay. When doing a t-test for the difference between two population means, the formula for the degrees of freedom is rather complex, and we typically use technology to help us calculate this, i.e. an online calculator or JUMP. Charlie Quick made this calculator, and it actually gets used by a lot of people from a lot of universities. More power to him. This is two sample. And I really mean this because he wrote up the script for it, and is it not coming up? Where's Charlie's thing? There it is. Someone else is beating him out now. They're trying to take away his web traffic. A lot of people have used this for a long time. Charlie Quick did an excellent job on this. And it's from the complex formula that we don't like to solve by hand. None of these are that formula. T-test degrees of freedom. There's some T-tables. Let's type in degrees of freedom first. Degrees of freedom. Too simple. T. There it is. There's our old friend. And yeah, I put this in the video. I remember now. I think I displayed it. I really wanted you guys to see everything, so we don't solve that by hand. It's not that complicated. I should memorize it. Because this looks like the standard error right here. And then you break up the standard error and square it, and then divide by that. That's just a mess. So I don't want to solve that. Don't got time for that. A type 2 error is always the most... No! Bad words. Is always the most serious. No way. Type 2 is not always the most serious because it's really all contextual. That's very, very false. First one was true. Second one is false. During the business analytics presentation, none of the classes got the business analytics presentation, but you can watch the Stephen Colbert video, Surrender to a Buyer Power. It's very funny, and it's basically this thing right here. Surrender to a Buyer Power. So you can check this out. It's all about Target and their analytics. Views 56,000. Wow, that's very low views for what I think is an amazing video. We show it all the time, but really didn't have a spot for it in the online class, and I didn't do it in the in-class class. So that is true. And Target knew that she was pregnant before her parents did. They actually sent this girl like stuff in the mail. She was like 15. Did you hear about it, Brenda? Yeah, it's a very famous thing. Like, so this dad called up Target, and he was like, "Why did you send my daughter pregnancy stuff?" And they're like, oh, we're sorry, sir, because they called him like 3 days later, and they're like, we're very sorry. We apologize. We have these crazy analytics people who think they can predict stuff. And then he was like, well, I had a talk with my daughter, and she's pregnant. And they're like, oh my, they're like, yeah, our analytics people are actually that good. We know you're pregnant before you do. So it's crazy. You got to watch Stephen Colbert. I'm not going to attempt to make his jokes, because that's, if you try to ever do a comedian's jokes, you just flatline. So check it out. Surrender to a Buyer Power. Amazing bit. Stephen Colbert doing late night. Check that out. Taking over from Letterman. A regression analysis cannot. Why is regression on here? I have no idea. Why is it on the third test? Oh, wait. It's because we're tying it into another topic. A regression analysis cannot prove a cause and effect relationship between two quantitative variables. Yet a chi-squared analysis, chi-squared test of independence, can prove a cause and a relationship effect. No, it can't. The only thing that can do cause and effect relationships is tests. So, no, not happening. Large chi-squared test statistics are more likely to lead to statistically significant results. That is very true. If we go back here to our chi-squared curve, should be in our history from what we've been doing all tonight. 1, 2 more back. How are we going to do? Aha! You see how this chi-squared right here, as it gets bigger, makes the p-value smaller. Larger chi-squared, smaller p-value. The null for the chi-squared is actually that it will land on 0, because the chi-squared is a right-tailed test. If the chi-squared lands on 0, you get your biggest p-value of 1. If the chi-squared gets really big, you get a smaller p-value. So the biggest p-value, which means you can't reject the null, is 1, and that happens when chi-squared is 0, because chi-squared is a right-tailed test. So we're just looking at differences, and it's a positive difference. Chi-squared starts at 0, skewed to the right with a center at the degrees of freedom. This is not a chi-squared with 200 degrees of freedom. It looks more like a chi-squared with 2. 3? It's chi-squared 3. That was not a 200 degree of freedom chi-squared. Don't need to know all the specifics of chi-squareds, but larger chi-squareds equals more likely to reject the null, because they go further out. For a given confidence level, or level of confidence, increasing the sample size will decrease the margin of error. That is, thinking about the way the formula works, I know the answer. Increasing the sample size will decrease the margin of error. That's very true. As long as you hold everything else constant, the more you sample, the better you understand things. Just theoretically thinking about it, the more you sample, the better you understand it. If I said, I want you to estimate the true proportion of free throws I'll make, I'm asking you to estimate how good of a free throw shooter I am. If I shoot 6 free throws, do you think you really understand how good of a free throw shooter I am? Probably not. I might make 4 out of 6, and that'd be really good for me. You're like, oh, you're a pretty good free throw shooter. We have evidence that you're, better than a 33% free throw shooter. Probably, the confidence interval is probably going to be way too wide then. I don't even think there'd be evidence of that, because we don't have enough samples to make a good confidence interval. If I shoot 100 free throws, do you think you could probably estimate how good I am? I'd say so. And your confidence interval is going to be tighter, because you're going to be more certain. If you look at the way the formulas go, you're dividing by n a lot of times. So n makes it tighter, and it's in the margin of error. So increasing n, if we go back to some of our formulas, decreases the margin of error. So we see here, this is a confidence interval. And so n is on the bottom. It makes the standard error of p hat smaller, which is going to make the interval tighter, which means tighter confidence interval. Let's see if there's anything else. That is it for all that. We've been going for an hour and 25 minutes. Does anyone have, I'm going to turn my mic back on, or my thing. Does anyone have any specific questions? Anyone specific questions? I'm going to stop screen.
I have a question for a previous problem that you just did.
Sure.
I can't remember which one it was. I think it was probably the one before the true false that we just did.
Okay.
And we got I think the P naught was 0.166 or something like that.
Mm-hmm.
And where'd you get that from?
Oh, good. Good question. That comes from where it says they want to test the claim to see if 1/6 of the accidents have teenagers at the wheel. That really tricked people on this question, because we didn't write out 1/6 or 0.166. It just says in at least one out of every 6 accidents, a teenager's behind the wheel. This portion right there. That's a good question. A lot of people, they're like, "What is the null?" And I'm like, "It's some value we're testing." And it's always hard to figure out what to say to students, because you don't want to say too much. I'm like, well, the null is usually associated with what someone wants to test, because it has to deal with the nulls and alternatives. So it's what we're testing. It's a null hypothesis. It's what you hypothesize to be true, what you're making claims against. And I have to watch words because, like, I think it says the word claims right here, claims. So that's a key in a key phrase. So usually I try to avoid some of the key words in the statements by saying, like, oh, it's something we're testing. Very hard to answer questions without answering them sometimes, without telling you what the answer is. You're like, oh, well, the null, that's got to be someone making a claim in the problem saying that this must be true, or they're saying they believe this. So you don't want to say it too specifically, because then I'd literally be in the, look at this portion right here. This is the null. But it's usually some sort of claim or something someone is testing out, or something believed to be true or stated. And even that is a little too far answering some questions sometimes. But it's the nice balance of kind of sparking something in someone's mind that they already know that they're just hung up on without actually telling them any new information. So it's tough answering students' questions sometimes. As I've taught more and more, I've learned better how to do it. Like, to be like, oh, well, the null value, well, what does that relate to? And they usually say, like, a test. And I'm like, well, think about what we might be testing here. Usually I try to have them give me the answers. And then I just say, well, what do we might be testing here? And then we're testing the value of 1/6. More questions. I could probably look up a probability problem. Let's say we went away from the MyPearson site. Was this our MyPearson site also long ago? It was. Exam aids. You do not have access to this course. Okay, guys, none of your MyPearson work counts anymore because I can't access the site. I can access the site. Okay. Do I have any people signed up for my course for the next semester? I got 6 people signed up right now for next semester. I want to see if they're actually doing some work. So we'll look at that later. I should send them emails and be like, great job, do all the homework. Like, I don't even know if I have assignments up for that course yet, because it's 2 weeks from Thursday, is it? Okay. So we're 16 days away. Yeah, I guess. Wait, is it that far? That's right. The 20th or the 19th? Something like that. Okay, let's talk more about the test. Okay. Here we go. Practice test 2, and no, go away. Don't like you. I will click on you if I want you to appear. This is transactions at the stadium. This is a question of note right here. It's a chapter 15 question. So let's write this down. Where'd our trusty pen and paper go? It disappeared. There it is. Hello, pen and paper. So this is a chapter 15 question, a module 14, I believe. Module 14, if I am correct. 128. This is a distribution question. Okay. Go away. So what we have here is that we're looking at the distribution of 200 transactions. And what we observe is a mean, well, this is what is known, excuse me. We know the mean to be 55. And let's bring up our notation right here. Very specific on the notation every time, because what we know to be true for this is a mean and a standard deviation. We know it has a mean and a standard deviation. What is going on? Insert symbols, symbol, like that. Why is it hiding stuff? Okay. So it has a mean and standard deviation. So the mean is 55 and the standard deviation is equal to, let's see here, the standard deviation is equal to 24. So, and I guess, let's see here. The sample size is equal to 200. Nice and neat like that. So with this in mind right here, imagine they took a random sample of 200 many, many times. Draw a rough sketch of what the distribution of the sample averages would be. This is where people got confused because the new standard error here, the new standard error is going to be, let's add in our old equation. It's going to be off my screen here. To get the standard error for this, we need to do under structure. We need to do sigma over n. So 24 divided by 200 equals the new standard error. And, oh, no one's yelling at me yet. I forgot. Brain is turning off a little bit. Sigma over the square root of n. Right there. So this is our formula right here for the new standard error of the mean. And we can calculate it right here. Take 200 square root. Copy that. And 24 divided by that. And our new standard error is 1.69. Copy that. And bring it over here and delete some decimals. Or, well. Well, I guess it rounds then. Okay. So with this in mind right here, let's just make it really neat. There we go. Rounds up. This is our new standard error for the distribution. And what we can do now with all this info is we can go over here to stat distributions. You might say to me, but Brian, I do not have stat distributions on the test. Very true, but all we're doing is just drawing the normal curve right here. We're not doing anything crazy. You just go ahead and 1.70, and we have a mean of 55. So we go here to 55 and put in 1.70, and there's our curve. Technically speaking, we don't really need anything plotted on it, so let's just put that off in there. So as you can see, it goes down 1.7 every time. This is the distribution of sample averages right here. Distribution of sample averages. Lot of stuff right here. So let's go back to our problem. That is the drawing of the distribution. At the bottom of the picture, indicate the mean and 3 standard deviations, with which numerical values label the mean standard deviation you made. Rounded to decimal points, we did that. Draw a rough sketch of what you expect the distribution, make it large at the very bottom, and then place that in. That's good. Based on your picture, indicate in the space below the value of a mean that you expect to see only 2.5% of the time, a value that large or larger. And this killed people a little bit because all you're doing for this one right here is, there's my buddy. Bring this over there. Go away. And so all we're doing right here is going up to this point. Because this curve is normal, according to the central limit theorem, or normal enough. So we're going up to 2 standard deviations because this is our 95. 95 is in the middle, and 2.5 is on the outside in each hand. So on the right, we'd have 2.5% of the values or higher above 2 standard deviations. So that's why we would expect above that to be 2.5% of the values. That is the answer, 58.4. What value in the decision tree? Decision tree stuff? Decision tree stuff's old for us. We did decision trees on the last test. Highest educational. Suppose that the company is able to randomly select report transfer. So this one right here, calculate the standard deviation of the sampling distribution. Okay, so let's do it. Let's do problem 3 because it relates to our test. We'll go through this. We'll do everything on the test right here. Problem 3. And let's write down what it is. It's another distribution one. And we're at 130. Okay. So they're trying to figure out the gender makeup of people that's the state high. The gender makeup of people that state their highest education level is postgraduate degree. So we randomly select 350 people with a postgraduate degree. The data show that 187 of these individuals were women and the rest were men. Of the 350 selected, what proportion were men? So to figure this out, we simply find out 350 minus 187 is 163. There were 163 men, and we now take, why is my brain going in reverse? There we go. 163 divided by 350, it's 46.57%. Now here comes the tough part, of the tricky part. Not so tough, but tricky. Calculate the standard deviation of the sampling distribution of the sample proportion of men in the above scenario if the population proportion of men with a postgraduate degree is 48%. A lot to say there. What we're saying is that the truth is 48%. So since the truth is 48%, the mean of it will be P times Q over N square root. The truth is 48%. We observe a P hat, but the truth is 48%. So what should we see if the truth is at 48%? We should see 48%. So that's going to be at the center of our distribution right here. The standard deviation is the truth right now. So let's go ahead and do 48 times 52, P hat, excuse me, P times Q over N. And was it 380? Was it 390? I couldn't see what you held up, Brenda. 350? 350. And then we divide by 350, and then we square root. So that is our standard deviation for the distribution of sample proportions. Standard deviation for the distribution of sample proportions. And what did we expect to see at the center? We go back here. We change this once again. At the center, we expect to see 48, and we have a standard deviation. And there's our distribution right there. Boom. All we had to do was find out the standard deviation for the distribution of sample proportions. And what did we observe? I think we observed 45%. Let's double check and see what we observed again. Number jumps out of my head. 46%, was it? I think it was 46, yeah. So here we are. Double check it. 350 minus 187 divided by 350. We observed 46.57. So just viewing this right here, 46.57 falls in here. It's going to have a z-score between 0 and -1. We already know that. We can actually find the z-score by simply going right here, taking the mean, which is P, minus P hat. I'm reversing it. I'm so sorry, guys. It's observation P hat minus mean, which is P. P is the mean of the distribution. It's a proportion, but it's the center. It's what we expect on average. So it's not really like a quantitative mean. It's what we expect on average. So it's not a quantitative mean. When I say mean right here, I'm talking about the mean of the distribution, not a quantitative mean. A little bit of confusion right there, but it's a mean of a distribution, the center of a distribution. There is the difference between the two. Or I just typed something in wrong because that doesn't look right. We take our observation, we subtract our mean, and there's the difference right there. The difference is negative like we saw, but now we have to do it standardized. So let's go ahead and take it and divide by the standard deviation, which we can see that we solved for earlier. And as we suggested, we fell somewhere in here, less than 1 standard deviation below, and not quite at 0. So we visualized it. We could take this value right here of 46.5 and go less than if we want to do it. It's like 46.5. I know that says z-score, but you have to use it this way. And there's our p-value. And we could have estimated something near this. It has to be less than 50, and it has to be greater than 16, because 68, 32, and then 1/2 in each hand of 32. So we can pretty much answer everything here right now. So to be able to say that it's normally distributed, we have to meet the 3 conditions. It's randomly selected. Good. Less than 10% is sampled. Good. And also that NP0 and NQ0 are greater than 10. NP0 and NQ0, or Q0 and P0 are basically 50%. And if you times those out, you will obtain values. 50% of this is, you're fine. P0 and Q0 times N are more than 10. So we are good. Regardless of whether you did it, just say calculate the z-score associated with it. We just did that earlier. Rerun the video if you need to see it. Or ask questions if you're confused. Does the z-score you calculate in part 4 make you think that the proportion of men who have a postgraduate degree is different than that? No way, because a z-score of greater than 2 might be odd. Like a z-score of 2 is more unusual, and we're nowhere near that. We're nowhere near 2 or 3. So this is negative 0.5 something. So once we say negative point, then you lost me. It's not that influential. It's not that rare. That's good. This is on sample. Oh no, this is a good one right here. This is on probabilities. So let's do it. Okay. Woo. Long review. Post this for other people to watch. Everyone's gonna watch it at midnight. Midnight tomorrow night. Ay, ay, ay. Down to just water again. Okay. For a certain candy, 10% are yellow, 5% are blue, 15% are red, 15% are green, and the rest are brown. You can assume that your candy selections are independent events. Good. If you were to randomly select one piece of candy from a large bag of type of candy, what is the probability you select a brown piece? Well, if the rest are brown, it's the complement of not getting the other pieces. So nice and simple. These ones weren't that hard on this test. We can just take 100%. It's everything but getting these other pieces, and we need to subtract 10%, 5%, bring this down, minus 15%, minus 15%. Everything but getting those 55. This looks like a crummy bag of candy. So the brown, it's like, oh, brown candies. It's like, why can't it be colorful? If you were to randomly select one piece of candy from a large bag of this candy, what is the probability you select a yellow or blue piece? When we say or, they need to be disjoint. You cannot select a yellow, blue piece and a yellow and a blue piece at the same time. It's not like you pull out a piece and like, oh, it's a yellow blue piece. No. So since they're disjoint events, they can't both happen at the same time, we simply add the probabilities. Probability of selecting a yellow is 0.05. Probability of selecting a blue is 15. Probability of selecting one or the other is 20%. If you were to select one piece of candy at random from a large bag, this was the probability you select a purple piece. This is 0. It's not there. These are easy questions. If you were to randomly select 3 pieces of candy, what's the probability you select 3 red pieces? And we say it's a large bag of candy because it's a whole bunch. And so the probabilities aren't really changing. The probability of selecting a red piece is 15%. So it's the probability you select a red piece, and then you select a red piece, and then you again select a red piece. Because you select one, and then you select one again, and then you select one again. And they have to be independent of each other. So it's not like all the red pieces are on top, or you start digging through. I don't know. You'd have to shake up the bag up. You randomly select. That's key to this, is that you randomly select. So when we say the word and, we multiply out. You say probability of this times probability of this times probability of this. It's and. So multiplication is the end word. Only a little bit more. It's going to be a fun one. If you were to select 3 pieces, what is the probability that you select at least one green piece? Now, this is what kills people. This is what kills people right here, and these questions are the toughest, but they're not that bad. Because to select one green piece, what is the only thing we're not interested in? So would it be all right if we selected 1 green piece? Is that at least 1 green piece? How about 2? How about 3? So the only one we're not interested in is 0. We can do anything but select 0. So how about we write it out? What we're interested in here is, in words, everything. 1 is everything. It's 100% probability. Everything but the probability, all green. We can just write it out like that. Everything but the probability, they're all green. Because that would be, it's like everything but they're all green. So that means at least 1 is a green. So what does this solve out to? Solving it out right here, the probability of all green is on our first draw, we get a green. And that would be 15%. On our second draw, we get a green. That would be 15%. On our third draw, we get a green. That's 15%. We get the same thing right here, and we take 1 minus it. And that's the probability they're not all green. Reading out what we have here, the probability of everything but they're all green. You can just read it. probability of everything but they're all green is equal to, no, stop it. So that is equal to at least one is green. Good stuff there. That is the trickiest that can get. Decision trees, and I think we might be finishing up. Probability, sampling, true, false. I think this is it. When estimating a population proportion, the 10% condition tells us that we must sample at least 10%. So false. So false. If the distribution of an individual values is highly skewed, a sample size of 100 or more may be necessary for the sampling distribution of the sample mean to be approximately normally distributed. True. We sometimes need a very large sample size for highly skewed data. That's the central limit theorem right there. Good stuff. Good stuff. Any last questions? Let me turn on your guys' mics. Any last questions right now? It's so hot in my apartment. Did you guys learn a lot from this review? Did it go pretty well?